So, hello, Michelle.
Hello.
We are here at Hugging Face headquarters in Paris, just outside of Les Halles. We got a beautiful view right on down there. How do I get one of these things or build one of these things? And what was the whole idea of the project in the first place?
That's a good jump
Yes.
into the next demo that we want to
Yes.
show you.
All right.
Yeah. So, okay. So, if you want, we can jump into the learning part to discuss a little
Oh, sure.
bit
Yeah,
about the algorithms.
absolutely. Absolutely. Absolutely.
So, one of the things that we had like a major release around a month ago. That was a project led by Adil, which is around implementing the reinforcement learning stack. So you see, it kind of has like
an idea of the hit it.
Yeah.
Almost got it.
So it does have some intentional movements.
The rest of the tour, and you are?
I'm Pepijn.
Pepijn, okay. All right, you've done something interesting with the arm. What did you do?
Yeah, so after we released the SO100, we also begin exploring mobile manipulation.
Up and down like ET,
like when you have
but it can't do this.
Neck ache, you can't move, you know?
Exactly. So there would be no rotation. You can do a rotation with a delta, but then you have to add a fourth axis, and then that becomes a bit more complicated. And then it's like a single rotation
and
this
it's
way.
completely decoupled.
Yes, but that is a clever solution. We're going to be back here, and the reason we're going to be back here is we're going to have the head back on here to see exactly what Mini Ricci is able to do. So,
yes.
Thank you, Caroline.
In a few minutes?
Yes, in a few minutes.
See you.
Okay. The same idea here is that if all of these motors decide to turn at the same time, you can get the wrist to spin around. You can get that normal movement. And then, so you can get, so you can get like all of them this way, will allow that to rotate around. And then if only some of them move, or if you coordinate them in a particular way, you can get a lot of range of motion. And we're seeing in here the actual ball, because what is so great about this mechanism, I couldn't believe it at first when I looked at the math, is it really does keep that platform centered at a point in space. I thought it was going to like move around and be challenging, but it turns out that's what it wants to do, which means you can just stick a ball there. So the ball isn't actually needed to keep it in place. It just naturally wants to orbit around that ball. But look at that toe box.
Yeah, it has a toe. Yeah.
Is that an actuated toe box?
This is an actuated toe box.
Oh, wow. Really?
It's known that we didn't have this one walk yet. Yeah, so this is the skeleton for the arm and shoulder, which would go like this.
So that would go there and here.
I think it's the other way around. It's like this side.
Of course, the other arm.
And then,
you put it on here, and again, open source. So, hello, Michelle.
Hello.
We are here at Hugging Face headquarters in Paris, just outside of Les Halles. We got a beautiful view right on down there. You must walk down that street every day for lunch and dinner, right?
Yeah, it's quite nice, actually.
I know. So, like you said earlier, it reminds you of the world you're missing when you guys are in here working so hard, right? Yeah. But you've got actually a very fun world in here of all sorts of different robots, which are open source. And can you just bring us through the whole process of how do I get one of these things or build one of these things? And what was the whole idea of the project in the first place?
Okay. So the main idea of the project in the beginning was really making robotics more accessible to all people that are passionate about learning about AI and robotics. And the way that we set up the project at Le Robot is that you can do it yourself. It's in a style where you can kind of like just everything is open source. The hardware is open source. The CAD files are open source. You can order the motors, and you can, if you have a 3D printer, you can either 3D print links, or you can also have the opportunity now to also order them from. There are like several companies that are packaging the whole arm that is pre-built. So you have both options. Really, you can either do it yourself, or you can kind of order it directly built. It depends on how deep you want to go.
Oh, okay. So that means in theory, if I want to, I could set up my own little company making these things and selling them.
Sure. Yeah. I mean, that's what that has already happened like 3 or 4 times. Because again, like from Hugging Face perspective, this part is not really like commercial. Like we are not selling SO100 arms. It's not really for profit. Anyways, like the arm is so cheap. Like there's really barely any margin for profit.
How cheap is the arm?
Well, one arm will cost you around $100.
Okay. Okay.
approximately.
Okay, so there's obviously certain things I have to buy.
Mm-hmm.
And so there's a supply list, most likely the motors and the actuators.
Mm-hmm.
Do I have to do anything fancy with the motors and the actuators, or do I just assemble them to the robot?
Not really. Like it's very pretty basic. Like you can just directly assemble them.
Okay, so
and like we had so usually the robots comes in two versions. You have like a follower and a leader, and the idea is that you're going to use the leader to teleoperate the follower. It's going to be very useful for data collections and for all kinds of tasks. So the first version we had, the SO100, to be able to teleoperate the leader smoothly, what we did is that we had people disassemble the motors and remove the gears so that they won't have any resistance while they are moving it. But then what we did, and this was like Pepine's innovation, which is like he kind of communicated with the Fitex, the company that manufactures the motors, and they kind of came up with a design with reduced gears for the leader. Which is quite nice because then like you don't have to actually do this extra step of removing the gears. At the same time, now the leader arm can actually have enough resistance to move around with the follower, which actually opens up a kind of a new space of possibilities. When we do, for example, we're going to show you a demo about reinforcement learning, where we kind of where the robot has to learn by itself to complete a task. But the fact that the leader can move the follower means that you can kind of take over and correct the behavior of the follower, so that you get like some data with corrective actions that will help you be more sample efficient. Right. So everyone understands the idea of the leader and the follower here is that they are dimensionally the same. All the offsets are the same. And here, obviously, you have a motor that's going to move this to a position that you want. And it's very hard for it to move because you have the gears that are in there that really don't want you to move it around. It's better to drive it that way. Whereas this way, you move this around, and these motors effectively become a digital protractor. They tell you exactly what the angle is between here and there. You send that signal over here, and this thing will then faithfully duplicate that angle, and then that angle, and then that angle, and that angle, and the result is this arm takes the same configuration. So I can sit back here with my eyes, look at what I want to have going on, move this around, and that robot is going to do that. And that is the way I can train it, correct? Okay, and so that's why these are going to be a little bit different. If I was to build this myself, about how long would it take? It depends. I think it will take you around an hour to build each arm. I think like with Pepine, for example, he has so much experience building arms. It takes him, like his record is 17 minutes or 15 minutes. Wow, 15 minutes. Okay, assuming I have all of the components that are there. But to print out the components, what are we looking at? How many hours? I think it will take around half a day, right? It will take you around half a day to print the body. Oh, really? Okay, so, boy, you must have a good printer. Mine's a little bit slower than that. Now, this can be printed on a standard printer at home, right? There's not anything really fancy. Yes. Okay, so if I understand the bed size, minimum 22 centimeters, and you can print anything. Yes. Okay, bigger the better if you want, and then that will work together. And it's just assembling everything. Any other hardware I need to have? Any like screws? Do all the wires, everything that come, are those separate items? Well, I mean, you have like the motor bus and I guess like the screws, but I think these are all like also very easy and very cheap to get. So they are all like available in the bill of material of the robot. So you get all the links that you need to order every part. Okay, so you get all that, and then for about $100, I've got something. $100 for this and $100 for that. Yes. Okay. Exactly. Now, I think I saw something earlier. Is there another interface that you have for this? Is there like an Xbox interface? So that is kind of yes, that's a good. That's a good jump into the next demo that we want to show you. All right. Yeah. So, okay. So, if you want, we can jump into the learning part to discuss a little bit about the algorithms. Absolutely. Yeah. So, one of the things that we had like a major release around a month ago, that was a project led by Adil, which is around implementing the reinforcement learning stack. So, the idea of reinforcement learning is that the robot will autonomously explore the environment, and it will start from a policy that really doesn't have an idea of what task it needs to do. And based on a reward signal, feedback from the environment, it will start adapting the base policy or the controller to go towards choosing the actions that actually perform the tasks that returns the highest reward.
Sure.
So this is a bit of a big problem. Typically, reinforcement learning in robotics, the issue with reinforcement learning is that it's very sample inefficient. Because you are starting from scratch, you will require a lot of data to be able to actually figure out. But there has been quite a bit of innovation on that side. There has been some sample efficient algorithms to be able to reduce the number of samples you need to learn a task. And recently there was like a work about a year ago called Human in the Loop Sample Efficient Reinforcement Learning. And the idea is to use these sample efficient techniques of RL combined with active feedback from the human, so that it kind of to give the ability to put the human to correct the robot's actions, which will provide you with kind of like better data to be able to learn quicker. So the big project that I was talking about, the release, was basically providing an open source implementation for reinforcement learning stack that allows you to learn tasks on the robot using this active interaction with the agent.
Okay, so just
and we can actually show you a task real time of learning actually a new task.
So just to completely dumb it down, I've got a robot that doesn't know how to do anything, and it's very simple. All I want to do is teach it to pick up this block in a bunch of different locations. So I would obviously put it down here with the follower in a couple of different locations, and then with the leader go over and just train it. Now on the end of the arm, we also have a camera, right? So you could either have a camera here, or can you have like a fixed camera also in some location? And so it's able to see what you're doing and then also do the policy of going over and grabbing it. And you have to grab a lot of data samples. About how many times do I have to do that before it will reliably pick it up if I just put this in some random location?
So this is a question that is quite dependent on how complicated you want the task to be. So I can tell you that with our implementation, we are able to do like pick and place tasks. So my cube is here and I want to put it there, for example. We are able to do that in around 10 minutes, less than 10 minutes of interaction.
Okay.
Yes. Given that our control frequency is around 10 hertz, which means you can do 10 actions per second.
Sure.
Let's say our episode length is around maybe 5 seconds or 10 seconds. You can see like around 10 minutes. It's not really a big number of episodes that you are doing.
And how limited is the work? Does it just have to be somewhere in here in any position and orientation?
So this is the kind of reason why reinforcement learning can be very useful. Is the ability to adapt to new scenarios. So if you can start like training a policy that picks a cube from here to there, the idea is that if you move the cube around, if it has access to explore the environment and get more data around these new situations, it should be able to adapt and also learn to pick it up from that cube, from that location.
Okay. And so once I've kind of taught it in there, it will be fine. But then if I put it out there, is there a good chance it will find that, or is that going to be very hard? Because it's sort of outside of the training domain.
Yes, for sure. I mean, the more you increase the training domain, it just means the more data you would need.
And that takes longer.
That will take longer.
Obviously. Now, normally, especially in real world applications, you try to make sure the world isn't too chaotic. You do like to have the parts kind of come in a normal area. It's just that sometimes we call it, corralling them to be exactly in the same location each time is a little bit hard. So if you can say, oh, look, it's just going to be in there. And then you're just saying like 10 minutes, that's not bad. To just say, that's all you need to do to sample that, because this is out of my data set. It's going, and not only that, this should be not in the set ever. I should never attempt to want to pick it out here for whatever task it is that I'm doing. So long as you keep it in there, that's reasonable.
I completely agree. Yes.
Completely reasonable. Okay, show us.
Okay. So Adil, if you want to start running. So we're going to show you a very simple task again, just so that we don't waste like a lot of time training. So the idea here is that you want to push this cube into the notch. Okay. So we found that actually this task is a bit more challenging than what we think, because you get a lot of situation where the cube is like that. And
I was going to say that I would rather pick it up and drop it there. That looks challenging.
It actually doesn't take longer to learn than the pick and place task. So it's but this one actually, like, since we have like really limited the space, it should be able to learn it in less than 5 minutes because we have a very limited space. But we have tried the same task on like on a much bigger space, and even though it takes longer to learn, it still learns it and achieves it. And actually, we have a very nice video about it tackling the cube as if it's like a football from right to left until it reaches the notch. We can show you like the longer.
Oh, that'd be great. Great.
Yeah.
Now, I noticed you put this here. It's almost like it's an obstacle that it has to go over to get there. So it can't cheat and take a shortcut, right? When you're training to go from here to there.
Exactly.
And occasionally I imagine the cube might hit that and then, you know, oh, that's a failure in the policy. You need to go up higher and come on down.
That is also kind of why we did it, is to make our lives easier so that it doesn't have to cheat. Because reinforcement learning, the funny thing about RL is that it will always try to take advantage of the dynamics.
Yeah.
So many times in simulators, for example, RL is a very good way to detect the bugs in your simulator, because if it can find a shortcut that is counterintuitive to you because you don't really think like that, it will actually take that shortcut and it will actually find a way to solve the task that actually doesn't make sense physically or dynamic-wise.
Right. Yeah.
So that we here put it actually just for our, so just so we don't go crazy with the cube trying to cheat its way without lifting. So yeah.
Okay.
So yeah, Adil will kind of show you like how we control this part. So you will see, what you will see is the robot trying to do random actions to explore the environment, but you will see also Adil from time to time using the gamepad to guide the robot into the achieving the task. And then you will see basically we can put down the gamepad and it will be able to do it by itself.
Oh wow! Oh, okay.
So here you see like it's trying.
So yeah, you're not picking, but you're trying to push it around.
Yeah. This is usually the fastest task we can do. So at each episode, we have to reset the cube to the initial position. The dream would be to do like some point reset free tasks where you don't have to reset it at all. Then you would need less human intervention.
Okay.
So we can have this as a success.
Yep.
And this gives the agent a feedback that it's successful. So when you see Adil dropping the gamepad, it usually means that policy is good enough to. And we take over only segments of the episode, so it's not like the entire episode is controlled by Adil. You can just give it pushes to say like, don't go there, just go. Ooh, so he can like correct the actions here to tell it like, don't go back.
Okay, so you're actually intentionally training bad episodes as well as successful ones.
That actually could help also to show it like what to do.
What to do is supposed to, also not what not to do.
So you see, like this was completely an autonomous episode where it kind of took it. But sometimes it tries to achieve the task and finds another variation where it doesn't. So completely autonomous. And to be clear, this takes the top view of the camera. So this is also vision-based, which was even very hard for reinforcement learning to do vision-based controllers. What is fun about watching this in real time is that you can see like how the controller tries different variants to be able to solve the tasks. Sometimes it approaches it from above, sometimes it's very quick, sometimes it's slow. So it's quite nice to see like the state space, how the policy space and how it's configured.
Okay, so some of this is man in the loop, you're saying? That it's autonomously trying to do it, and then you're correcting whatever it's doing wrong.
Yes, sometimes. But you see like the last 3 ones have been completely autonomous.
Okay, now you're correcting, trying to show the student the correct technique.
So it kind of starts figuring out more and more.
It's getting better, yep.
So.
Okay, so now just to prove that the dice is not loaded, you want me to give it a random location?
Yeah.
All right, so I'm going to go ahead and I'm going to go ahead and take that and then let's see, put it, I don't know, something like that. Let's see. How's it going to do now?
It's correct direction.
Okay. It's going to see that.
Quite here.
We can like do like a few minutes on that location to see how it can adapt to this kind of movement. See if it can cheat, it will cheat. Like.
Oh yeah. Exactly. Just got to understand the right way to get it in there. Okay. So now that you understand the motion that's going on, is that you have a controller here, which basically gives you X, Y, and then another control in Z, perhaps?
Yeah.
Okay. So these are purely Cartesian locations. And as you can see, this is not a joint input. It's not like you can control this axis, and that. That's what this is doing. And so what a human operator would be doing is they're grabbing this, and internally we're sort of seeing how we want to move it, and based on the motion that we're seeing, we kind of like what we have and we can feel it. But that is basically an input device that has got 6 degrees of freedom.
Yes.
Or actually, I guess it's a 5-axis arm plus the 6-axis, which is the gripper.
Yeah.
So that's basically a joint mapping to a joint mapping. That's very easy. That's a one-to-one mapping.
Yes.
Very simple to do. This is a bit more mathematically challenging because you're really saying, take an XYZ location and now calculate the joint values. And that's what we would call inverse kinematics. So in a sense, this is like a forward kinematics. You give me the joint solution, I just copy it over here. The other one, you've got to do a little bit more math to do it, which is why you have the controller is there. Yeah. And these are 2 different ways of doing it, and really good ways of being able to explain to people why the math is so important to be able to take Cartesian locations and then convert them into joint space.
Yes.
Do you have something on the screen to show us for the simulation of this?
For the simulation of this, we can show you we have the same setup simulated for a panda arm, where we kind of use it as a test bench to test if the reinforcement learning is.
Yeah, because I assume there's something crunching on over there on that computer.
I can show you basically. So this is actually an interesting point. So one reason why this actually works so well is because we have what we have is a learning an actor-learner server architecture. So typical reinforcement learning. So this is a bit technical, but typical reinforcement learning, what you do is that you collect a data set. You run your policy rollout to collect some data. You get this data, you update the policy based on what kind of returns you got, and then you collect some more data.
Sure.
What we do here, and what HILSERL, the technique I told you about, does is that it decouples the acting and learning processes. So the actor has a version of the latest policy, and it's just collecting data all the time.
Sure.
And you have another server on another machine that is just taking this data and just learning. So they're kind of a bit separate. So one has a bunch of data that it keeps updating the policy on, and one is just has a version of the policy and updates the version of the policy every now and then to just roll out and collect data. And this architecture actually also allows us to learn in a much quicker way than we used to in the single stream setting.
Okay.
So yeah.
So now, is Adil's laptop somehow connected to this, or is that not part of the?
No, that's not part.
Okay, so basically everything is being done here.
Everything's being done.
And you say there's a server somewhere else?
So right now we are running both, because this machine is big. We are running both on the same machine.
Okay.
But you can have 2 computers to do that.
Okay, but basically this machine is big enough. You're not using anything else. It's all right here.
Yeah.
So you've got obviously some GPUs in there.
Yeah, one 4090 GPU.
Okay. So you have an idea of what it takes now. In order to do that at home, once I build one of these things, would I need something like this, or would I just go ahead and use a service?
Well, you would need a GPU, some kind of GPU compute to be able to do that. Whether that's through a service, or whether that you have something locally.
I have a laptop that has
a GPU
on it. Yeah,
that should be enough.
And that would be enough. Okay. So I don't need really any fancy hardware. I mean, this is impressive. I'd love to have this at home.
Yeah.
I'm not sure about the electric bills, but yeah, I think that would be.
We have even trained policies using the camera from our phone, so you don't even need a fancy camera to be able to do that. Just using the cameras from your phone should be.
Okay. So basically, you can do everything at home, and then learn how to train policies, do some real embodied AI kind of examples.
Yes.
All right. And you can build it at the same time. Yeah. So in a sense, that means you can own the whole stack. You are the manufacturer of the bot, of the different components. You're putting them together. You're understanding the supply chain needs that are going on. You're then going ahead and teaching it a particular policy for a problem that you have. And you also are able to do everything in-house with your own nets, all that.
Exactly.
Okay.
Yeah.
That's a great way to understand the entire process.
Yeah.
And then of course, in the real world, this stuff scales up to a ridiculous level that you can't make the stuff at home. You've got to go out to some other supplier to be able to produce it, all these other things. But at least you get that big picture understanding of what's involved in actually building a robotic arm, what's involved in training a robotic arm, what is reinforcement learning?
Yes, exactly.
What the steps are involved, and how much compute. Because for a lot of people, they might be thinking, I need one of these huge server farms, because all we see is like all these very large server farms that everyone is using for training, what OpenAI has, what XAI has, all of them. And you can imagine there's no way I can afford that kind of compute.
Yes.
Only to realize that, no, you can do it on this, but the reality is you could also do it on that, right?
Yes.
If it has a GPU, you could probably do it without a GPU. It would just take forever.
You can do it on the MPS also if you have a Mac. Yeah.
Right, but it's a good idea to have a GPU.
Yes.
And then you'd be able to, in a reasonable time, be able to see what's involved.
Yeah.
Okay.
That is a big reason why, for example, for when we build our RL stack, we really didn't focus on the classic reinforcement learning techniques that require like very heavy computations to collect like a massive amount of data to train a policy. We were really focused like, okay, I have my robot, I have my local setup. Is it possible to train a policy with as least amount of time as possible with my limited setup?
Yeah.
So that's why we really focused on implementing this technique, because it makes kind of like we did with the robot and the robotics, it makes also like people wanting to learn about RL for real applications more accessible.
Yeah. Yeah. I think anyone that's interested in this space should just do it, even if it's just as a hobby.
Yes.
Because now you understand exactly what the entire process is like, what has to be done. Then you can come up with your own thesis of like, how far away are we from AGI?
Yes.
Well, actually, I should ask you, what is your opinion? Are we months, years, or decades away?
I've never been asked that actually, so I've never really thought about it. I think like the thing is that because I've worked for so long with robotics, I still have the feeling that the technology still needs a few years to be able to get this moment where like the same moment like we got, for example, with ChatGPT.
Right.
So I think for me, I don't know in terms of like giving a quite timeline. I mean, if I had to do it, I would probably say we're still like at least half a decade away. But I personally, I don't.
You know what the
really
safe answer is I'm asked this question all the time.
Yeah.
And rather than giving a date, I just say not this year.
Yes.
And I'm always right.
That's probably
that's the best way. But
I'm gonna steal that way.
Yeah, exactly. Now the other way of thinking of the problem is that, you know, AGI will just be able to do everything. But in order for it to be useful, we don't need AGI. It just has to be good enough. And for many people in the space, they've already kind of had their ChatGPT moment because they realize it is kind of good enough. It's just that the public hasn't been able to see it yet, where they're going, because that's what the ChatGPT moment was, right? The public saw it, but there are a lot of insiders that probably years ahead of time already saw it and said, oh, wow, this is absolutely incredible.
Yeah.
So do you think, from the standpoint of these techniques being really usable, are they already usable, or do you think we are just very close to them becoming usable in the sense that we can start training robots to do useful work, and that in the end of the day, having that robot do that work is actually the same or cheaper than a human, and I'm getting the same output, the same quality, everything. What's your feeling? Are we there, or are we still a ways?
I mean, I think we are still away. I think we are not there yet. But I think, you know, especially when you work closely with these kind of techniques, you can see that there is potential to do many things with them. And I mean, especially when you're working with the robot, like we have actually had community members, whether was it through like the hackathon or whether like in our projects, because we have a lot of community members that participate in our project, we have actually had a lot of people reproduce many things that we're doing. But to say that we are ready for like a kind of general AI that solves robotics,
that's a ways.
I think that's
I'm still thinking it's like very narrow use cases.
Yes.
That you train it for something specific, and it's like, we might be close to being able to do it, and it's just a question of, you know, the actual cost and reliability, everything else. That the fact that you may have this huge infrastructure around there supporting that one robot, because you're not sure if it's working yet. But that's my prediction, is that we'll see that before 2030.
Okay.
And then a lot of the other stuff you could probably say in the 20s. So there I am, I'm kind of dating, but again, it's like not this year, and then it doesn't necessarily mean next year or the year after that. So I will be considered an Nostradamus when I'm right again. Then so you did talk about the hackathon. So that's the next thing we're going to go along is the hackathon was done with Ricci 2, and there was groups like all over the world that had a weekend that they went in and they found what different sort of applications and what they could do with it. And so at some point we're going to take a look at the Ricci around here, elsewhere, but we've got a big tour to go on through this office.
Just to be clear, like the hackathon was mainly done on the SO101 arm.
Okay.
It wasn't really done on Ricci 2.
Okay. So it was these arms.
Because these arms are really like the in terms of like accessibility and price, this is like the best way to be able to have this kind of large-scale international hackathon. This is the best way to provide people with robots is by using the SO101 arms. So people were using the SO101 arms.
Okay. Okay.
But we can show you like around.
So we got a lot. So we've got Ricci 2 in here, and we've also got the mini Ricci, which is going to. I don't know if that's going to be the beginning after the miracle in editing that goes on here that Mauro is able to do. I'm not quite sure what the order is going to be.
I think we can like maybe Pepine and Caroline. But if you want, we can check on like on the policy.
Okay, let's take a look.
So now it's like Adil has dropped the controller, so he doesn't even need to intervene. So now the robot just knows by.
And if you rotate it just a little bit,
it will fail.
Okay, so at that point you didn't have enough training data to be able to do it off. So it was like close to parallel. Now the thing to point out is that you are not relying on any previously taught information. It was completely wiped in the whole time you're going through and trying to show it how to move that in there. Okay. And now you get to go in and give it another data set.
Well, the thing is that all the data that was collected online are there. So it kind of keeps learning from all the interactions.
Okay. All right. Oh, got that one.
So you see, it kind of has like
an idea of the hit it. Almost got it.
So it does have some intentional movements.
Now, as far as the mechanics of the arm that's here, sometimes a robot is pushing really hard. Does that throw it out of calibration, or is it able to hold it pretty well?
I don't think we've ever had issues with that. Like it's able to be stable enough.
So once you assemble this thing, you go through some sort of calibration phase. So it knows where everything is, and you don't have to worry about necessarily slipping or losing a zero reference, because if you did that, then your data might be a little bit corrupted, or is it difficult for it to recalibrate after that?
Yeah, I mean, probably yes, you might need to.
Okay, so imagine I come in and I said, I'm going to replace this motor. Take it out and put a new one in there. If I calibrate it and figure out exactly where the new zero is, will the old data work?
I mean, you can have like yes, I mean for sure, because we have changed our calibration process a couple of times, and you can have like just a formula to convert from old calibration to new calibration.
And of course, I could then take the result here and then move it to one of those arms over there. Okay. What, quote, identical arm. Now, so all the arms are the same size. Do you have any that are slightly different size, or like a longer second axis or a shorter first axis? Have you ever tried that?
For this specific arm, no. I mean, we just have like this one design.
It could be interesting to see how easy it is to then transfer the policy to an arm with different lengths in there. And it might, hopefully, it's just a matter of recalibrating it and letting it know. But this is end to end, right?
Yes, end to end. But this is also based on, as you said, like the actions are in the end effector space. So you can theoretically kind of try to say like, okay, I have this policy that works on this robot, I'm going to transfer it to another one, but work where my policy is controlling the end effector.
Okay, so you are telling it where you want the Cartesian location to be. You're not telling it where you want the joint values to be.
So yeah, when you see Adil controlling the gamepad, it's actually controlling the displacement of the XYZ of the tip of the grid.
Yeah, that's important, because now you've got a generalist policy here.
Exactly.
Yeah, the arm itself, the kinematic configuration arm doesn't matter. So we could have a completely different style arm.
Yes.
Yeah, we could have a Cartesian arm.
Yes.
We could almost have a mobile robot doing the same thing.
Yeah, I mean, when you see like the work on, for example, like on the new foundation models for robotics, if you heard about vision language action models,
yeah.
So you usually have like large scale data sets that have different embodiments. They have different robots. Even some robots have like wheels and can navigate. In some way, like learning magic, it finds a way to actually learn a good representation, given all this data by training on all these kind of like large-scale data sets.
Yeah, and I think it's in some cases like a lot of the humanoid bots, their end-to-end, I believe, is actually like going right down to the joint manipulators because their models are so complex, and that becomes a lot harder to move from one embodiment to another.
Yes,
but in this case, yeah, it should be straightforward. It's not always as straightforward as you think, but
it's always
in theory,
it
should. Yes, yeah, something unique about that arm that makes it challenging to reach a certain location that you expected. Okay, great. So, are we ready to move to the next station?
Yeah, Pepine, you want to?
Okay. Okay. Ready?
Yeah, I'm ready. We'll see.
Okay, so we're back here for the rest of the tour, and you are?
I'm Pepijn.
Pepijn, okay. And all right, you've done something interesting with the arm. What did you do?
Yeah, so after we released the SO100, we also begin exploring mobile manipulation. So not only providing the community with an easy and affordable way to do manipulation tasks, because it's just a robot, but also providing them with a cheap and accessible way of learning policies that can also navigate. So we basically added these 3 omnidirectional wheels to the SO100, and the platform is called Lakiwi. We developed it with the community together, with some students from a university in the US, and it has its own battery. It has 3 more actions it could take, which is in the X, Y, and rotation space. And then in a similar way where you can teach the arm to do something, you can now also add those 3 extra actions, and you can also teach it to drive around while doing these actions.
Sure. So you have this as a coarse manipulator to get it to some far distance, and somehow it has to figure out how much I need to move this, and this becomes your fine positioner to get whatever it is that you want to either grab or location you want to go to.
Exactly, yeah.
Now, the locomotion is interesting because you've got 3 wheels. I've seen 3-wheel MRs, mobile robots before, but we've noticed they're 120 degrees apart. They're not kind of straight ahead as you would expect them to be. And I know the Ricci robot has also got an interesting wrist where everything is 120 degrees apart. So are you being inspired that you're trying to get out of this orthogonal world and say, hey, what if we make the world 120 degrees instead of 90 degrees?
Yeah.
And of course, when you do that, your wheels have to be different. So an omnidirectional wheel means like right there, you'll notice I can spin these. So it's not that these are for traction, but you also have to have rotation this way and some this for the slip.
Yeah.
So if I'm going straight, this is weird. Both these are going to move together. Obviously, if only one of them moves, that thing is going to kind of want to turn.
Yeah.
But if they're both moving themselves together, it's going to result in a vector this way, but it means you're going to get a lot of slippage there. And of course, this one's going to drag. Yeah. But because it's got that, there's no problem. It goes. Now I see there's like a phase offset here. I guess that's just there, right? So you always have something in contact no matter where you are, right?
Yeah.
Yeah. Okay. So they don't move in different directions. They are linked together. Yeah. So you have 3 motors for that. So what are the advantages to having 3 wheels that way versus the traditional way?
Yeah, so that's a good question. So the first one is we wanted to keep this robot very cheap and doing it with just 3 motors, which will reduce parts, which will make it a little bit more cheap. And then the second advantage that you can have, and that you also translates to bigger robots, for example, Ricci has the same setup, is that you can now, just like a human, also move sideways. Whereas if you have a setup with, for example, 2 wheels or 4 wheels, you need way more motors because you need to have each wheel be able to turn in a direction.
Right.
So when you're thinking about AGVs that for example, have two actuated wheels. If they need to do something next to a table, for example, they need to go in there, go back, go in there, go back.
We all know what it's like to parallel park.
Exactly.
It would
So
be
that's
nice to
another
have the side to side. So what that means is that, okay, you've got a motor that can actuate your wheels going forward. The thing is, I need to steer, which means I have to turn the wheels to be able to do that.
Yeah.
The other, if it's only a two-wheel base, it's going to be very unstable. It's going to fall over. So by having the third one on there, we have a stable platform and some interesting ways to be able to literally turn on a dime.
Yeah, exactly.
You could just spin right around there. And again, you get, because of the omnidirectional nature, it's very easy to parallel park and come in, as you say.
Yeah, exactly. Yeah. So from a mechanical aspect, that's very, very useful. And it's a very cheap and accessible platform for everyone in the community to also learn mobile manipulation and to, if you already have an arm or not, explore explore this side of robotics that is a bit different.
Right. Now the first question a lot of people would ask is, well, wait a minute, that's such a great idea. Why don't we build cars this way? And I think the main thing is like, this is designed for maneuverability. It's not really designed for speed.
Yeah, exactly.
So if you want to go very fast down a highway, and also, I mean,
you're slipping.
There's going to be a certain amount of slippage, so it's not ideal. But there's all these other advantages. And think about it. A lot of times, you could of course use differential steering if you just had two wheels, which is kind of what you're doing here, forward. Or like you say, you can turn the wheels that way, and that would require another motor. In some cases, you might have a system where both wheels move with the same motor, and then they have something else to turn it that way. But that means you have only one motor for forward progress. In this case, you have both motors for forward progress, so that might give you a little bit more speed.
Yeah, exactly. Yeah. And then you need more motors, of course, because you need a motor to turn the wheel itself, and you need a motor to.
Okay, so that's rather interesting. I like that because it makes you realize there's more than one way to solve a problem. And this is not a solution that most people would have thought of.
No, it's been done before. Of course, it's a long history in robotics, but
it's not that popular. It's not something that people would always see. They always see the more traditional approaches, and that you're looking at this and saying, okay, consider this. Oh, right. Some other examples that you'd like to show with this and how this works?
To be honest, not a lot, because we don't have it running right now. But yeah, it's another way and another accessible platform for the people that use the Robo and want to explore and learn more about this technology.
And I can build this myself, or is this something I have to order?
Yes. Okay. So if you already have the arms, you can print also this, and then buy the motors and the wheels and the battery, or bring your own power bank, maybe even.
Sure.
And it's around the 300 euros then an additional to the arms. And then you can also explore the mobile manipulation side of things. Yeah.
Okay, so maybe you can go around and pick up my house before the Roomba comes through the vacuum.
For example,
Yeah, exactly.
And you need a little bit more data when you're doing mobile manipulation, because of course your camera is not static, it's also moving throughout the space. But the interesting thing is that with the imitation learning policies that we have in Robo, so the AI policies that try to learn something end to end, you can try to replicate almost what all these, for example, Tesla is doing with their automatic taxi, etc. Replicate it just at home, or try to understand the technology better and try to...
how navigation works. And then there's the other thing is, the system has to make a decision on how to get to some location that you want. So it's, like I mentioned, there's coarse positioning and then there's fine positioning. So I want this to pick up the socks on the floor. It has to identify a sock, and it has to make the decision, can I reach that, or do I have to get there? Now, we can go through all sorts of math to sort of figure out whether it's reachable or not. We do it by intuition. So I know if I want to get this coffee cup, I know I can just reach to it. I don't have to move. But if I want the one over there, I know, oh, I can't reach. I don't even have to think about it. It's just native. I come over, I do the course positioning, I get myself to a location that I know I'm within reach. Now I'll go ahead and I can pick up the coffee cup. So that's the same thing is going on here, I guess, with your reinforcement learning, right? It's able to intuit when it has to move, and it will figure out how to get there. And does it know when it's close enough? Or is there some other algorithm you were using?
Yeah, so it will learn that from the data. We only have run imitation learning, so imitating human expert policies or human expert demonstrations on this. But yeah, you can, for example, also do something similar there with RL to have it learn something.
Sure, yeah. So the math way is that we figure out what the XYZ location of that thing is with respect to my origin, and then I calculate it with my arm and say, oh, that's out of reach.
It is almost more end-to-end.
Yeah, so yeah. And that's how we would do it mathematically. Oh, it's out of reach. How out of reach is it? Oh, it's about 1.5 meters out of reach. Oh, okay, I need to now move my base to be within whatever the reach bubble is that I have. And then I'll go ahead, move myself, and now my arm is there. That's the algorithm that we use, the heuristic algorithm. Yeah. But again, we don't do that. I mean, that's
exactly.
As engineers, that's how we solve the problem. Yeah. As people, we don't. I just know, oh, coffee cup's over there.
Exactly. Yeah.
It just happens, doesn't it? So that's the same thing with your imitation learning.
Yes,
it just happens.
Yes,
cool.
That's what we're trying to do. Cool. And of course, the more data you have, the better it works.
And it's something. It's something about that. My vision system is looking at that, and from their perspective, the coffee cup looks too small to me, and that's some sort of signal to me that you've got to get closer until the coffee cup becomes a certain size I know. Oh, that's the size that I can usually reach.
And then, of course, it has to somehow know what a coffee cup is. Yeah. How it can look. What are all the different shapes of a coffee cup? And have an understanding of the world, of course.
Right. So, and then you can do those weird optical illusions that magicians use all the time. That you can have like this really big coffee cup that's way over there. You think you can reach, and you realize, no, I can't get it. And you have to kind of know, oh, that's a monster coffee cup as opposed to a normal size one. But with that, I'm assuming that's kind of what the RL is doing, is this idea that it can feel scale the same way we feel scale and solve that problem without actually relying on real math.
Yeah, so it is recognizing a bunch of features that it got already in the data, and then it has some kind of signal depending on what the camera currently sees and the state of each joint, and based on that it will predict the next action.
Yeah, the next action. Okay, that's great.
Yeah.
Thank you very much.
Yeah,
and that's rather interesting, and
we can
ready to continue the tour.
So I'm working. I'm going to put the head back, so it's not because it's Bastille Day that we're going to behead all our robots, right?
Right.
But yes, this is a very interesting structure, as you say. This is what we call a Stewart platform. Very known type of parallel robots, which are known for their dynamics and also their precision.
Yes.
But also for their complexity as a computation.
Extreme complexity. So what we see is that there's a platform right here that the head's going to go on, and we want the head to be able to move. Now, normally a head, we'd like it to rotate left, right, pan, tilt, rotate, and that's a 3-axis problem. But if you want the head to kind of go back and forth, like I think you showed that video with the guys that would kindly do that dancing, we need to have translation in the X, in the Y, and in the Z. So we need complete rotations. Now, at first it might look like a Delta robot, but the thing about a Delta robot, all it can do is like move in a plane and it can go up and down, but it can't change the orientation. But this is a Stewart platform, and a Stewart platform is used in like flight simulators. So they're very rigid, they're extremely strong, and you can put a whole cockpit up there and you can move everyone around, and it's like a roller coaster ride. Now, they are limited in the movement. We can't go all the way around, but the same with our heads. We can only kind of bobble them around so far, but they're extremely stiff. And they also are used in like certain kinds of CNC machining because of their rigidity and everything else in there. Now, the one thing you did say is the kinematics for them, they're parallel kinematics.
Yes, this is a mess.
It's a mess to solve. It's really hard to solve. And yesterday, I saw that there was a claim that Grok 4 is PhD level. And the first thing I did is like, Grok, give me the forward kinematics for Delta robot. And it went through, and believe it or not, it did it. It said, oh, the analytical can be done, but it's really tedious. I'm going to do a numerical. I'm like, no, I don't care if it's tedious. You're an AI. Go ahead and do it. Then I said, do it for a Stewart platform. And it was like, it's really, really hard. It's actually, it claimed that there was like an analytical solution, which I could not believe because I had never seen it in my research.
No.
But it said they are. But there's so many different solutions, like 40 different solutions. It's actually quicker to do it numerically rather than checking all of your analytical solutions. So have you discovered the same thing?
No, I mean, so far I haven't. I don't think that's even possible. I mean,
Yeah.
for me, it's another constraint problem that
Yeah.
does not have a solution. So you
Yeah.
have to run it numerically,
Yeah.
and hopefully you'll find a solution to your
Yeah.
kinematics.
So maybe we proved Grok is wrong. Let's find out. But it is really challenging because it's all these nonlinear equations that just kind of come together that are very, very hard to solve. But the numerical solution is not that bad, so long as you have a good starting guess. So,
yeah, exactly. It's the same for inverse kinematic, actually.
Yes.
If you have like a standard SO100 arm and you want to run the kinematics, the inverse kinematics, if your initialization point is too far from the solution, you can fall directly into local minima and then you're stuck.
Yeah.
No, this is the beauty of kinematics, right?
So that's interesting. So what that means is that you actually have 6 little motors in there.
Exactly. We have 6 motors in there to get the 6 degrees of freedom, so rotation and translation. This is what makes Richie Mini so expressive, because it can do all this motion, dance moves. It can also go down when it's off, where it slips, and then up when it's woken up, and then go like this and this. So this helps with the expressivity of Richie Mini. And I think if it was just a delta, it would have been less impactful and less appealing for people.
Yeah. If it was just a delta, it could only do side to side, up and down, like ET.
Like when you have
but it can't do this.
Neck ache, you can't move, you know?
Exactly. So there would be no rotation. You can do a rotation with a delta, but then you have to add a 4th axis, and then that becomes a bit more complicated. And then it's like a single rotation
and
this way.
it's completely decoupled.
Yes. Yeah. And normally you think of neck movement as being more rotation than translation, but we do have that with our spine to be able to do that. So that's an interesting application of a Stewart platform. That was not my first guess. So it's
no, me neither. But when I saw it, I was like, this is maybe the first real Stewart platform I'm going to see at everyone's house, because as you mentioned, it's mostly something from either in the industry or the simulation platform, like when you have a cockpit simulator or something. So that's not something that you see in everyone's kitchen, and soon it's going to be a reality.
Yes, and everyone's going to be talking about Stewart platform. Now that Stewart platform is spelled with a W, as we know. There's like 2 different ways of spelling Stewart, so it's S-T-E-W-A-R-T, and it's extremely rigid, which means that if you try pushing that, if the motors didn't move
if the
because
motors
they're
were
reacting,
on,
if they decided to lock themselves in there, that would just not want to move. Now, right at each of these joints here, I believe these are spherical joints, aren't they?
Yes, exactly.
Yes, they have to be, because you've got so much movement going on there.
And then you will not fall into singularity all the time, because if you have the constraint of just a single rotation on this point, then you will just be stuck and cannot move, because if just one motor is slightly ahead of the others, then you get
binding. Exactly. So that's the complicated thing.
This is the best way to illustrate what a singularity is in robotics.
And so when you lock those motors down, it just stays in position. It requires a lot of force to be able to move it out, which is why they like it for CNC machining. So a lot of CNC machines will use it for what they call 5-axis machining, because it is very, very stiff. The thing is, it has that limited rotation. It can't do a full hemisphere or sphere. It's not even a hemisphere. It can do a little bit. So you can do some complicated surfaces with it, which you might use it for, like propeller blades or something like that, or a prop for large
hot
ship.
wires and stuff like this. Yes, this is what they do. But in this situation, I think they mostly use it for the dynamics properties, because all the motors, they're located at the base of the robot, and they're not in the head or propagated along the kinematic chain, so that you don't have the inertia of the motors. And having this base motor, that has to be super huge, because it holds the whole structure in place.
Exactly. So this is like an example of that. As you see this poor little motor down here, it has to carry kind of the weight of all those when it moves. So in this case, it doesn't necessarily have to carry it gravitationally, but it does have all the inertia of that when it tries to move. This motor here, of course, when it tries to go up, it's got to support that motor, that motor, that motor. And this is what we call a serial link mechanism, because each link is carrying the motor. But if you can put all the motors down at the base and find some way of being able to then manipulate it that way, you have a huge mechanical advantage. And that's what's going on, is that all the motors are down here, and none of the motors are actually moving with respect to the base. They always stay fixed.
So that you can have this like very fast motion without the burden of having inertia and maybe too much torque in your motor.
Exactly. So the only thing you have to move is really the platform here, plus these little arms, which are very, very light. They can be a lot of times they're like carbon composite or something like that.
Exactly. That's something you can do.
And then so you have very light mass. It can move really fast, really fast.
Or you can see Delta robots moving in the future. It's super impressive.
And I said this before, I will say it again. Do you know what inspired the Delta robot?
No.
Chocolate.
Seriously?
Seriously. They were trying to solve a problem in a chocolate factory in Switzerland on how to take the pralines off of the conveyor and put them into little boxes. And again, and that's another example of taking parallel kinematics. And because it's parallel, the math is really, really hard.
It is.
The math for this is really easy.
It's already a bit hard. I mean, the longer the kinematics chain gets, the harder it gets. Yes.
But still, once you understand that you're just multiplying matrices, it's more. I say it's more of an arithmetic problem than a math problem. So forward kinematics is arithmetic, inverse kinematics is math, and this is
the other way around.
More than math. I mean, that's the next level up, because it's virtually, it can't be solved.
No.
I mean, analytically,
it's like you can write down the problem as an optimization problem, but then you don't have the certainty of the solution to this problem.
Right. The easiest thing is just hand it to a computer, let it iterate, and come up with the answer. And if Grok is right, then
maybe
it could be that the numerical solution is actually faster than the theoretical analytical solution if one exists. Yeah, I think in some Euclidean plane way out there, abstract place is like this solution to the problem.
It lives over
we
there.
mere mortals just can't get access to it for some reason.
Yeah, because it's not as popular as you say, the serial kinematic chains, which are very widespread in the industry. We have this vision of the robotic arm, which is an arm, and that's a platform supported by several.
So the main reason for the platform is its strength. It's very, very fast. Because of the parallel kinematics. The downside of it is it has a very limited work envelope. That's the real problem.
Also, that's
why you tend to have these serial link mechanisms, because they are able to have a much bigger work envelope, but then they come with the fact that you have to have a bigger payload capability.
It says in everything, you have this Pareto front where you have to pick one solution over the other depending on what you want to do.
Exactly, how you want to optimize that. But this is nice because it fits in there quite well.
Yes.
I think it's probably the only 6DoF head that I'm aware of out there on a human. There may be a couple of cases here and there, I'm sure, but most of the humanoids are choosing to be either 2 or 3 axes, just rotation. A few have gone with 5, but that's like actually additional rotations. But I guess you could put that additional rotation and kind of got some head bobbing movement around. But that is a clever solution. We're going to be back here. And the reason we're going to be back here is we're going to have the head back on here to see exactly what Mini Ricci is able to do. So thank you, Caroline.
In a few minutes?
Yes, in a few minutes.
See you.
Okay.
Thank you.
You're welcome. So at some point we want to do fabrication.
Yes.
It's an open source. I can download the CAD files and then I can print them.
Print them on these printers, yes. Yeah, so a part of being accessible is also having the people fix their own robots and make their own robots. It helps in decreasing cost, and I think 3D printing, especially in the last 5-10 years, has made very big steps in being accessible, very cheap. And the community is also, a lot of them are open source and collaborating together. So yeah, a lot of parts for the SL100, for Ricci Mini also, and for the Kiwi, the mobile robot, are 3D printed, and you can replace and build them yourself.
Okay, so this is similar to the Creality that I have. This is what 22 centimeter by 22 centimeter, and probably 22 up. So that's a sufficient size bed. This is obviously a smaller one that's probably a bit too small. Some of the parts I'm sure you can do on there, but the bigger ones maybe not. These printers, they're under $1,000, probably a couple $100 depending on what you want to have. And it turns out the filaments that you get, I'm surprised that they're not that expensive either. So
yeah, I think a roll is currently like $20 euros, maybe even less.
Yeah, and I think in some cases less. So you can do that. You can print it out in about 12 hours, which is reasonable, but you're going to have to come and change the parts probably every hour.
No, so you can print one arm on one bed.
Okay.
We try to make sure that that's possible.
All right.
So you can basically print the robot arm in one go and then assemble it, which is
just about everything on one go. Really?
Yeah.
Okay.
It just fits.
I was assuming there'd be like 3 or 4 tries. Okay. Now, when it's open source, meaning I'm downloading probably an STL file,
Yes.
And then I have to use my own slicer because everyone has their own slicing software.
Yeah.
Okay. Yeah. And then that becomes a little bit of a trick of trying to figure out what are the best parameters to put in your slicer.
Yeah. We have some recommended settings.
Okay.
Some people also uploaded the already sliced file,
Okay,
so G-code file.
Great. So if you have a
for-
certain printer, you can get it.
Yeah.
Yeah. Yeah. It is always a question of what the bed temperature should be, what the nozzle temperature needs to be.
Yeah, exactly.
Also, whether you need to put down rafts and all these other structures.
All these things.
Do you have like a lot of complicated structures that come around there? Or is it able to print
No, I think
fairly
the
easy?
wrist is the most complicated
Okay.
one, but we try to keep it simple.
Yeah. Yeah, I know, because I found that the structure sometimes is when the whole thing fails.
Yeah, exactly.
Yeah.
But I also noticed, I had the Ender one, I think it's one of the first 3D printers of there. And even within iterations, especially I think the last few years, there's still been a big software improvements in terms of automatic calibration, etc. So like the user experience is way much better.
It's much better. Absolutely. Absolutely. Okay, so that's all you need to be able to print everything out. That's great.
Yeah.
Did you print out the Hugging Face logo here, or you had that made somewhere
We
else?
already had that somewhere else.
Okay, there we go. There we are. Okay, great.
Yeah, we can go around the corner.
And here we have.
So here we have Richie
Hello.
2.
There we go.
And a part of the Hope Junior, only his legs and its upper body.
Okay. Okay.
Yeah, but we can I can say a bit more about this if you want.
Okay. Well, so this is Ricci 2, right?
Yes.
So it's a 2, which means there was a Ricci 1. What's different?
Yeah. So the Ricci 1 was also developed by Pollen, a French company that just joined us about a month ago. So they joined Hugging Face. And Ricci 1 was also a fully open source robot. It was, I think, less capable in sense of the payload, etc. It had. So this is really a more industrialized, reliable version, I think. And we also have one here to integrate with our library, the Robo. And it has some, from a mechanical standpoint, some very interesting transmissions and kinematics, I think. Pollen is really keen on these smart ways of doing kinematics, and it's maybe you want to dive into that.
Which is what I like. So we just took a peek at the Ricci Mini. So anyone who's getting the Ricci Mini, they're going to recognize the head is very similar, maybe a little bit smaller. What's going to be very different is how the head articulates in the Ricci Mini. So there's a Stewart platform there, where here you're using a special kind of wrist, which is a 3-axis wrist and is like almost delta-like, but it's a different approach, which is really quite novel. And of course, it's used down here in the wrist as well. So in Ricci 2, I've noticed that there is actually what looks like a ball and socket right down here in the wrist, whereas you have the actuation mechanism here, and you have the servo stack right up here. So these 3 servos stack together to move these different links. And again, it reminds me of your little mobile robot that you have these 3 wheels. And you have to coordinate the 3 wheels together to get certain kind of actions. So if all the wheels spin together, you can spin around this way. But in some cases, you can have just 2 of them spinning, and it will go forward this way, and the other ones, you can move them around. The same idea here is that if all of these motors decide to turn at the same time, you can get the wrist to spin around. You can get that normal movement. And then, so you can get, so you can get like all of them this way, will allow that to rotate around. And then if only some of them move, or if you coordinate them in a particular way, you can get a lot of range of motion. And we're seeing in here the actual ball, because what is so great about this mechanism, I couldn't believe it at first when I looked at the math, is it really does keep that platform centered at a point in space. I thought it was going to like move around and be challenging, but it turns out that's what it wants to do, which means you can just stick a ball there. So the ball isn't actually needed to keep it in place. It just naturally wants to orbit around that ball. And of course, you have this little center right there, and now you can run all your services right through there out to the hand. So we don't really, as you can see, there's no wires here sticking out. They're all inside of there.
And it's a bit based on like a vertical rolling joint,
Mhm.
where you basically just as a human also have two spears just sliding over each other.
Yeah.
But then in a vertical kind of way, where you simulate it with the kinematics of the joint itself.
Yes. Yeah. So that's so you've got 3 motors right here, each of them independently moving one of these links. We coordinate those links, and I think you've put your hand in there in a particular way that we tend to have more range of motion in one direction than we do in another.
Yeah.
And I think you've set it up that to make sure that you have the maximum range where we want the hand to behave kind of in the pitching direction for the human, but this way it's still, that's still not bad.
Yeah.
It's still really very, very good. It's surprising how much reach that has. And are there any situations where it locks up or doesn't have much strength, or is
I'm
it?
not that familiar with the exact details of the Ricci 2 kinematics, but I think we've heard a lot of positive things about it.
Well, there was a paper about this wrist written by one of your colleagues over at Pollen, and he used an analogy that I keep stealing that I really like. If you, me, and Marwa decide that we want to go over and, I don't know, pick up the couch that's up front, what I can get on your shoulders because you're stronger than me, and then Marwa would get on top of my shoulders, and then the 3 of us would try to lift up the couch.
Yeah, exactly. Yeah.
Or let's say Marwa would try to lift up the couch. So she has to be strong enough to lift up the couch. I have to be strong enough to lift up her and the couch, and then you have to be strong enough to lift up me, her, and the couch.
Yeah.
That is how a serial mechanism works.
Yeah, exactly. Yeah.
But if all 3 of us decide to go around the couch and pick it up from different sides, it's very easy. That's the idea of what's going on here, is that all 3 of these motors are always working together in whichever direction you want to move. So you never have one carrying the load of the entire wrist, and for that matter, carrying the load of the other actuators.
Yeah.
And again, another natural location to put this mechanism right up here.
Yeah.
So now this is open source, right?
Yes.
So how do I get one of these? It doesn't look like something I can build at home.
sells these, but a lot of the design is open source.
Okay.
I think still the easiest way to get one is just to order one from Poland.
Order one. Yeah, I was going to think about it.
But all the design and how these mechanisms actually work, you can find on the Pollen website.
Yes. Yeah, I don't have a CNC machine at home. I imagine I could attempt to print some of these things out, but they'll probably break in no time. Now, the other thing I'd like about this is sort of the novel approach is that this is a 7 degree of freedom arm, which is what the human arm is. And a lot of times when people break the problem down, they break it down as like a 3 plus 1 plus 3. So you get a 3-axis shoulder, 1-axis elbow, and a 3-axis wrist. The reality is that might be the way you solve it mathematically when you think of it from the kinematics. But from the standpoint of the mechanics, people look at it a different way. So even though you have a 3-axis shoulder, usually it's built as a 1 plus 1 plus 1 because it's a serial stack.
Yeah.
And then you have like a 1-axis shoulder or elbow down here. And then a lot of times the wrist might be like a 1, 1, 1, basically serial, or a 1 plus 2. So like the Optimus wrist and the Apollo wrist are the same way, where they have a parallel kinematic there. What you've done here is to say, wait a minute, we're not going to be a 1 plus 2. We're actually just a 3. So that wrist is a 3.
Yeah.
No doubt about it.
Yeah.
Up here, you kind of have a 1 plus 1, but you're really thinking of the shoulder as a 2-axis problem here.
Yes.
And you're thinking of the elbow as a 2-axis problem.
Exactly.
Because everything is kind of down here. And really, you can think of it that way. It's like, is this movement that's happening here happening up here at my shoulder, or is it happening down here at my elbow?
Yeah.
Kinematically, it's the same. It doesn't matter from the math, but mechanically, how you build it may be a different mindset on going in how to solve the problem. Because we shouldn't be solving the robot as a actuator problem. We should be solving it as a joint problem.
Yeah.
How do you solve the shoulder? How do you solve the elbow? Do you consider the elbow a 1 or 2-axis problem? And how do you solve the wrist?
Yeah.
And of course, in some cases, the way the wrist is solved, if it's solved as like 2 axes down here plus 1 in front of it, it's almost like the elbow is 2, except it's here and then the second one's down there. Whereas in your case, the first one's up here, the second one's down there.
Yeah.
So it's a different approach. That's what I like about Ricci, is that it's going to make everyone think about how to solve the robot problem a little bit differently.
Exactly, yeah. And which is, of course, also very important. And the way Pollen did this is very elegant, where you shift all the loads, like the heaviest components, which are often the motor, of course, back towards the body itself. So as far away from the gripper where you minimize in the terms the inertia of the moving arm, so the flying load basically.
Right.
But you also need less strong motors because one, with this mechanism they cooperate, and then two, because you put them higher up the chain, they have to move less weight.
Exactly. That's the whole idea, is that if the actuators have to carry other actuators, they have to become very strong, which means they become heavy, which means it's self-defeating. So
Exactly.
again, going back to that analogy, is to have three people lifting up in parallel.
Yeah.
The person at the bottom is just going to have to be a beast. Going to have to be super,
Yeah.
strong. But if we decide that three of us together, we can all be really wimpy and weak, and the three of us together would be able to pick it up more easily than three of them stacked together. That's the same thing. So now these motors can be a lot weaker, which means they're a lot lighter, which means this can be lighter too, because it has to carry such a heavy stack down there and it just keeps on going all the way and up the stack.
Yeah. Exactly.
Yeah, that's great.
Very,
That's great.
very elegant.
All right. And so it's mobile to move around?
It actually has the same, a similar platform as the mobile
okay.
I showed you earlier.
It seems like 120 should go in the name somehow, because it's just like 120-degree offsets everywhere, here, there, and there. Yeah. All right. So
very clever.
Yeah,
robots.
thank you. Now you have another bot over here. I don't know if there's much to show.
Yeah. It is missing its arms, but we can maybe go a bit deeper into the arms, which are a little bit further developed later. But yeah, we showed this at the Humanoid Summit. This is Hope Junior, and what we really want to show is that besides these little robots that are in the library and that you can use with the library, we're also actively, especially in the coming weeks, but also we're now at a point where we also can support multiple more advanced robots, such as a humanoid, such as full degree of freedom arms and hands, using the same technology and using the same software stack. So we're really actively trying to make these more advanced robots also way more accessible and open to the open source community.
Yeah, and we can see is like, the big challenges here is you get a bipedal robot. And look at that. Look at that toe box.
Yeah, it has a toe. Yeah.
Is that an actuated toe box?
This is an actuated toe box.
Oh, wow. Really?
It's known that we didn't have this one walk yet. So it's really an experimental
okay. So you get
way of seeing. So it's really an experimental
okay. So you get
way of seeing how can we build an open source, good and cheap robot.
Yeah, I think a little bit there and there.
Yeah, but we think that an articulated toe box is also a very important thing for walking.
Yes.
At least I believe that is.
Yeah, so it's not articulated; it's actuated.
Actuated.
So there are articulated toe boxes out there, which means they do have a joint there, but they're kind of spring loaded, and they just will bend a little bit and then push back. Whereas this one here, you've actually put a servo in there, so that can move quite a long ways.
Yeah. I think you have some great videos about why it should be an intuitive thing to add to a robot, but I completely agree that it, especially maybe for more advanced use cases, where you really want to push the limits, could be used by adding a toe.
And as we can see, it's not like it's a huge bulky actuator like some of these others. It can be small enough. It doesn't have to really lift the whole robot, but just be able to at least change the configuration of the toe, maybe lock it in. So yeah, that's always things to think about. Is how many degrees of freedom do you need? How many are too much? How many are too less? And the trade-offs. And the only way we're going to answer that question is we have to experiment. Nobody knows. Just keep experimenting. Okay, good. Now, you talked about the arms aren't here. What is the business end of the robot?
The business end?
The business end of the robot.
So we can maybe move towards.
So we're going to go and take a look at some hands.
Unfortunately, the creator isn't here today.
Okay.
But here we have, I think they're a bit butchered by a lot of tests. But here we have the hands of the Hope Junior arm. We actually just, probably when this video is online, have released the arm and the hand with all the step files, everything you need to build it yourself, on GitHub and on Hugging Face. But yeah, you can dive into a bit. It's a tendon-driven hand, designed by Martino, one of our colleagues, and by Rob, from the Robot Studio.
Okay. Now, so on the thumb we have like our additional. These are tendon. Okay, that's tendon-driven.
So this is where the wire runs through, and the motors are all up here.
Right.
In the wrist.
Right. So it's going to be like your bicycle tubing that you need to have that, and the tendon's going to come through here.
Exactly.
And now you've got this tendon. Oh, so no, that's a spring.
The thumb has one here.
Yep.
And then 1, 2, 3.
Yes. Okay. So we should be able to maybe see the tendons through here.
Yeah,
how they're going to close it. Yep.
So you see there.
Yes. Yeah. Okay. And so that means you can control each of these IP joints sort of individually. We can see that there are springs back here, which that does the extension versus the flexion. So the tendons will do the flexion through here. Yeah. And then on this side, we sort of have the same thing.
Yeah. Yeah, so the fingers are the same actuation mechanism, all the same, different than the thumb a bit. Where they also have one to actuate the first 2 degrees of freedom, and then 2 here to be able to do the.
That's what we call the abduction.
Yeah.
Yes. Okay. So, I think that's the abduction right there. Yeah. Now these come through here, but that doesn't move down there in the palm, does it? No.
Yeah. So they're not big drivable because the motors are in here and it's a joint.
So we have that here, and then we're able to go back and forth. So you have a tendon here and another tendon there that pretty much is going to make the fingers go back and forth.
Yeah.
One
so
to
each
go
finger
this way and one to go the other way. Right.
And then also, if you pull them at the same time, you'll get this motion.
Yeah. You could. Yeah, that's right. You could use it differentially, which means if you pull them together and then maybe offset it a little bit, you could get kind of abduction flexion at the same time.
Yeah, exactly.
Yeah. And then you have the spring back here, which is going to be opening up.
It's the passive.
So it's a passive extension. Yes.
Yeah. And then you see that the joints themselves are also rolling joints. So you don't have any bearings, but you have this rolling mechanism where the wires wrap around the joint on both sides, which makes it rolling, and which also makes it, it is challenging to design, but it makes them very robust because you can just slap them, nothing happens, nothing physically can break easily, except the wires, of course.
Right, and then the main thing is trying to get the mechanical advantage with the tendon, so having that rolling joint helps a little bit, bring it around. Okay, so in this case, all of the actuators are back here in the forearm. I think there's some in the palm as well, it looks like.
A few, I think 4 or 5.
Yeah. Now, this is what becomes kind of a challenge with the human, any sort of hand, is that as you move things back here in the forearm, that means your tendons somehow have to snake through your wrist joint here and basically through your metacarpals to get them in there. So there's, or basically what's a carpal tunnel, which is where they all sort of run through, and you need to do it in a way that doesn't get exposed. And of course, as you move your hand really far this way or that way, we can see it's kind of causing these tendons to want to move.
Yeah, move a bit.
And that's creating tension or compression in there, depending on which way it goes, which means the system has to sort of adapt and realize that, if I move my wrist, one of my fingers is going to start to move along with it if I don't compensate. And then, of course, there's the other thing is that movement there can cause these tendons to wear out, which is why we have something called carpal tunnel syndrome, that if you are always typing like this, your tendons don't like that, right? Yeah, exactly. Okay.
Yeah, and it's so, this is also fully open source now. So we're really wondering how the community will build their own versions of it, and will experiment it, do experiments with learning, actually grasping policies, etc. with it. So you can also, in the same way, download the STL and step files, print them, assemble them according to a tutorial, and start doing more advanced robotics.
Sure. Any touch sensing in here?
No, not yet, but there are a lot of ideas on how to do this.
So one way is like using the back driving of that, of sort of sensing whether the tendon is tensing up a little bit. You might be able to backfeed it that way, and then that means back here somewhere you're measuring that in the motor. And we talked about that earlier, but off camera, that what you were doing with the little robot
Yeah.
is that you are able to do torque sensing, but you don't have torque sensors.
Yeah, exactly.
Yeah.
So with the SO100, with our mainstream robot, I would say, we're trying to add force feedback, torque sensing, or actually current sensing, to measure also the torque that the robot feels almost indirectly through the whole drivetrain, and to also feed that to the AI policy. So to also learn, besides position, just like all these other big robotics companies doing, besides position, also learning the force that's required for a specific task. And we hope to also bring that to these accessible robots. Yes.
So how challenging is it to map torque or current to torque? It's not a one-to-one relation, or do you even bother mapping it to torque? Do you just kind of look at the current and say, oh, this is the level I want it to be at?
So if you have a good current sensing sensor, it is kind of linear, because you have the back EMF from the motor. If it's a DC motor, you have the back EMF, and then you can figure out how much, so the current and then the torque that it produces is kind of linear. So you just have the torque constant. So if you can really, in a really good way, sense the current of the motor, they can indirectly know the torque that the motor is outputting.
Okay.
But the tricky thing is also with these cheap robots is that because the drivetrain is not perfect, it's not super stiff, it has some backlash, etc. It's a challenge and a trade-off between, is it feasible for these cheap robots and drivetrains to do, which is where the learning part can really help, because you're doing something end-to-end, and the AI can understand a lot of things.
And that's when they started talking about this idea of torque transparency with your actuators.
Exactly.
That if you have a lot of slop in the drivetrain, it's sort of hiding what the actual torque is that's being applied to the other end. You have to guess what that might be, and that means you'd have to model that drivetrain, and that becomes very difficult.
Exactly.
If you have something that's more what they call like the QDD, the quasi-direct drive, then you can almost make the assumption that, oh, whatever the torque is in my motor is the torque that's actually being experienced at the joint.
Yeah. So I'm a big believer in that principle also. For myself, I like to imagine like a pool noodle. Sometimes as a child you had like these pool noodles, and you can imagine trying to actually do something with the pool noodle, but because it's so flexible, you don't really know where the end is, even though you're controlling it. So you can also see, take the same metaphor in these drivetrains, where you have very high inertias, for example, which are already in movement, and you don't really know where the output is. So making that transparent is very important for getting torque.
And making sure your control system is able to understand that and adapt. And we know that from like cars, that if your steering wheel is very, very loose, it's very hard for you to control the system because the feedback is horrible. Exactly. You're moving one way, you turn it this way, and it doesn't react in time, and then you overreact. You try to go back and forth, which is why a lot of cars, I think they have like oversteering in it because it's sort of better for our control system as a person as opposed to being very, very loose. Yeah. So again, that's the same problem that you have, is if you can't measure it directly, if you're getting really bad feedback, it's very hard to control.
Yeah, and it's a key component, because if you can do it this way, you don't need to have pretty expensive torque sensors, and you can just solve it with the parts that you already have, which is the motors themselves.
Right. And then eventually I can see that you do want to measure it that way anyway. And then if you do put sensors on that, that's just some additional data that you can use as like additional feedback to sort of figure out, how do I close this entire cycle?
Exactly.
So I wouldn't even just rely purely on a torque sensor if I can already get the current as well. I would try to have them work together.
And I think a good addition to this is when you have this kind of drivetrain that is low inertia or very transparent, it also acts as like a passive safety feature almost, because it can sense things, it can stop quicker than other robots. So,
exactly. And for trade, and you were talking about one example that, I don't know, maybe if we want to look at it over there, that for certain teaching applications, the force feedback is actually how you want to train a problem.
Yeah.
So it's not so much following a path as opposed to applying a certain amount of pressure on a path.
Yeah.
And that the robot has to adapt to that, and force feedback makes the problem very, very easy. I remember seeing like a polishing application. This was done years ago, KU Leuven, using a very old school robot, which was a Cincinnati Millicron robot. And they were first looking at that idea of force feedback. coming from the end of arm tooling, and they want to polish a windshield going back and forth. And the way you would train it is that you have to train all the different points and you want it to follow a certain trajectory. Well, that's what I might do if I was going to say doing water jet cutting, where I have to follow a particular path. But on the windshield, I don't really want to follow a particular path. I want to apply a certain force.
Exactly.
So it turned out all they had to do is teach a start point and an end point. And they said, robot, go from here to there. And as you're going along that path, make sure you only apply a certain amount of force in the downward direction. And the robot adapted. And they actually get this very complex motion out of the whole thing without having to teach the complex motion.
Yeah.
And of course, you could imagine that depending upon the buffing wheel you have, it wears down over time, right? Which means the distance or displacement you have is going to change. What if your windshield or your part's a little bit different or placed a little bit different? Easy as that. So that's one of the advantages of force feedback, is it can actually make your job a lot easier.
Yeah, exactly.
Yeah, great. So thank you very much. All right. Any other goodies to show?
There's a Hall sensor in there which acts as the magnetic encoder, basically.
Oh, wow.
So there's a Hall sensor in there, a Hall sensor in there, Hall sensor in there.
All right. And from that, you get the kinematics and this. So that would just fit right on there. Oh, and that would be the one for the thumb.
Yeah.
Oh, so it's the wrong hand.
That's the other end.
Yeah. So we would have it in this hand. Yeah, that's the complexity that you have to do to be able to do proper teleoperation.
Which is also, this is also open source this week, actually. So
this is a more accurate way of being able to track what your hand movement is doing. There's no doubt about it, as opposed to trying to do gestures. Sometimes the gestures are off, but this can be pretty clear. But at the same time, you have the problem that my hand and your hand are different.
That's true. Yeah.
And you almost have to scale it to be closer to that. But at the same time, do we want this to match my hand or your hand, or do we want this to match that hand? and the reality is, I think we want that to match that hand there, since that's the thing that's doing all the movement. And then it looks like this is also for training.
Yeah, you can pick it up if you want.
Okay.
Yeah, so this is the skeleton for the arm and shoulder, which would go like this.
So that would go there and here.
And I think it's the other way around. It's like this side.
Of course, the other arm.
And then
you put it on here, and again, open source. So we'd be able to get my elbow, shoulder joints there. And again, you're just reading my joint values here and then feeding them right back into the robot. Yeah. And this makes more sense for arms that are kind of my scale. If you want to be doing joints, you'd want to do it this way. If you're doing Cartesian, you can just do it with a hand controller and a VR setup. But in this case, it's faithful to the kinematics of the robot, which means you can control the robot more faithfully. Yeah, these exoskeletons. So cool. Absolutely cool. And then those are the bots we're trying to control.
So by because we're doing it open source, we also really believe that the problem that we're trying to solve is such a big of a problem that we almost can't solve it in one company or one entity. So what we're really trying to do is gather everyone in the community, research labs, people that are interested, companies all together, and trying to solve robotics and AI together. So trying to share the data with each other, trying to share as much as implementations with each other, and hopefully in this way we can enable everyone to build on top of this technology and also to profit from this technology. And that's really it's one of the most important goals that we have.
Right. In the end, it's all about data. And no one can collect all the data. You need a lot of people out there being able to do it. So that's the advantage of open source. And that is the philosophy of Hugging Face, right? It's always been about open source.
Yes.
Do you want to talk at all about that background and why open source beats closed?
That's a hard question. I'm not sure if I can dive too deep into it, but in terms of robotics, I think it's such a fundamental, important technology that it is important to share with everyone, and also that it's such a hard problem maybe that it's not solvable if we keep very close and not collaborate with everyone together on it. And I mean, it's also more fun, I would say, to collaborate with everyone on it. So that would be my answer.
Especially when someone gets a breakthrough and everyone goes, "Oh, really?" And then you can just everyone start chasing that.
Exactly.
Yeah. Okay. Great. Thank you very much for the tour.
Yeah. Thank you.
Okay.
Thank you for coming by.
All right. So I'm not sure if there's much else, but it's been an interesting visit here at Hugging Face.